Hello, James Flaten here. I'd like to talk about using OpenRocket, in particular using OpenRocket when you have a model already, perhaps one that someone else has drawn, one that you found online. And so how I might look at a model, try to evaluate whether or not it's complete enough for my use, and possibly make some changes to it. So let me share my screen. And this is the model that I have in mind. This is the rocket I have in mind to play with. It's the Lock Precision 4-inch diameter Goblin. And it turns out that this particular kit comes with a RockSim file. So RockSim is a .rkt file, and I'm not using RockSim. I'm going to use OpenRocket, but I'm actually able to open this file with OpenRocket. So let me get OpenRocket running. Interestingly enough, OpenRocket is a single click, at least on my computer. So if you double click it, it will open it twice. Single click, I'm running version 24.12. Just downloaded it, slightly new to me, so a few of the menus look a little different, but I hopefully will be able to find my way around. And I'm not going to use all the features. Let me go and open. In my downloads, it doesn't show anything because it's only looking for OpenRocket files. But if I ask it to show me everything that's in my downloads, I do find this .rkt file, and it will open it. And it looks a little odd. Perhaps that's because whoever modeled it did some things that I don't understand. Perhaps it's because the conversion from OpenRocket, from RockSim to OpenRocket, messed things up a little bit. I'll fix it. The first thing I'm going to do actually is I'm going to save it. And when I save it, I'm going to save it as a .ork file. I'll just leave it in my downloads for now. So now I have essentially what I would consider a native OpenRocket file. Let me just get this out of the background here. And get this out of the background as well. And let's look around. So first of all, this is a single deploy rocket. So it has a nose cone, and as I click on these things, they will highlight. So it has a body tube. It has fins. It has, that's the aft centering ring. There's the middle centering ring. There's the forward centering ring. You know what, I could rename them to make it a little bit easier, but I'm not going to edit them anyway, so I'll leave those alone. It has a body tube. It turns out this is the motor mount tube. So let me actually double click on that and rename it motor mount tube. And if I click motor, this is checked. That's good. This is a motor mount. That means OpenRocket will note that if I choose a motor, put it inside of this tube. Okay, so now I have a better name here. It has a parachute that's up there. This one I don't understand at all. Shock cord mount. Sticks out the bottom of the rocket. I'm just going to delete it. And then it has a shock cord. I would say the parachute and the shock cord aren't quite in the right position. I will look at the details of all of these items. But I do notice there's a couple things missing. In particular, missing are eye bolts that would attach the shock cord to the nose cone above and to the upper centering ring below. So I will add those in a minute. I also noticed that a couple things here have these extra icons. These extra icons mean that these items have mass overrides on them. That just means that someone, whoever made this model, said, here is my shock cord, and this is what it actually weighs. OpenRocket calls it mass, but it's actually weight. Here's what it actually weighs, and so I'm going to override that. It's probably true for them, but I'm going to turn off all of the overrides and then just make sure that the materials are reasonable, and then the weights should be reasonable. And then for final polishing, I might go back and actually put on some overrides. If I had the device in front of me, I do not. Just saying, you know, that eye bolt really is 1.05 ounces, not 1.0 ounces. And so I will tweak it just a little tiny bit. Let me take a look. So first of all, let me look at the shock cord. I'm just going to go from the bottom up. So here's the shock cord. And one thing I noticed about the shock cord is that it's using a custom material. Whoever drew this model put in their own shock cord, and presumably this is exactly what they wanted, but I'm going to choose from the regular menu of shock cords, and I'm going to choose tubular nylon 14 millimeter shock cord. So that's slightly different density. I'm going to change the units of length to feet, and I'm going to say that 20 feet is sort of excessive, so I'm going to try a 12-foot shock cord. I'm also going to notice that the shock cord right now looks like it's overlapping with another part, the motor mount tube. So I'm going to push the shock cord up. Oops, wrong direction. Push it up a little bit. That's about where it would sit. And I would say for 12 feet of shock cord in a 4-inch diameter rocket, that's about the size. It's perhaps 2.4 inches long and full width wide. That's about as much space in the rocket that the shock cord would take up. So I'll leave that alone. I'll call that okay. But oh, let me go to the override and let me turn off the mass override and let me turn off. Ooh, notice when I turn off the mass override, it changed the mass from 1 point something to 2.06. That's what it thinks is a more appropriate mass for the amount of shock cord and the type of shock cord I've chosen. Turning off the center of gravity override as well. Okay, done with the shock cord. Let's take a look at the parachute. So the parachute also has overrides. Right now, the parachute is set at 3 ounces. I'm going to turn that off, and it goes down to less than 2 ounces. I'm going to turn that off, and let's look at the parachute. And let's say that this is a 36-inch diameter parachute. I don't know why it was 35 point something. Let's say that most of the other things are fine. Let's say that the packed length of the parachute is, I'm just going to make this up. I'm going to call it 3 inches. It's quite possible it won't be that big. And the packed length is more or less full diameter of the rocket. And let me just shift it so it sits right on top of, what have I got here? Maybe about 6 inches, maybe about 6.25 inches. There it is. So the parachute in this case is sort of right adjacent to the shock cord. And I've already turned off the overrides. Oh, and I want to make sure that this goes off at apogee. For a single deploy rocket, I'm going to set the motor to fire at apogee, and then I'm going to let the parachute come out at apogee. Okay. So here's a centering ring. This is the top one. Presumably all 3 centering rings are the same. Take a quick look. It looks like they're basically a 1/4 inch thick. I don't know why it's slightly less, but that's close enough. They're made of plywood. That's good enough. But it's a custom plywood. Perhaps I would have chosen wood, birch plywood. Has a slightly different density. While I'm at it, why not say 0.25? That's what I would think my plywood would come in as a 1/4 inch thick. And that's a reasonable place for it. Okay. And the other two, I won't even bother adjusting. The adjustment I made was very tiny, a slight adjustment in density of the kind of wood. Let's look at the motor mount tube. So the motor mount tube is, first of all, the inner diameter in millimeters. This will be a more recognizable number. This is a 54 millimeter diameter motor mount tube. That's fine. They claim it's made out of paper. Not really sure what it is made out of, but it's probably paper, cardboard, something like that. I guess I will leave that alone. And it's rather long, but maybe that is legit for this model. I don't have it in front of me, or this particular kit. I don't have it in front of me, so I will leave that alone as well. Fine, 17 inches long. Wow, that's excessive. Okay. The fins, there are 4 fins. They're made of, I'm going to change this to birch plywood. And I'm going to say that I don't think I'm going to get aircraft sheet metal quality surface finish on them. I'm going to call this smooth paint. It's actually possible that it might even be rough paint. Notice down here is a place to put fillets, and the fillet radius is set to 0. In other words, this is not doing anything. The fillets certainly aren't made of balsa. They would be made of epoxy. That's something you could come back and do a bit better job on later. Turns out epoxy is not one of the choices in the menu for materials, and I'm not quite sure what the density is. I could look it up. So I'm just going to leave the fillets alone, but technically you should have fillets in here. I'll say okay. And then the body tube. Let me look at the body tube. Again, I don't think it's likely to be that smooth. perhaps smooth paint, perhaps regular paint. I think the body tube is actually likely to be made out of cardboard, not paper. And I will leave the rest of it alone. Notice down here, I can click on a part and get it to open the edit menu directly. So this happens to be a nose cone. The override is turned on and it claims that this nose cone is 5 ounces. And if I turn that off, it goes up to 11 ounces. So this is a massive difference. One should check whether or not 12 ounces or 5 ounces is more appropriate. But right now, this nose cone is chosen out of a parts library. And OpenRocket thinks it's probably in the vicinity of 12.8. I'm sorry, where's the mass? 11.2, right down here, 11.2 ounces. But whoever made the model actually slimmed that down to 5 ounces, perhaps because they were using an alternative nose cone. That's fine. Again, I think this is probably too smooth. I'm going to go with smooth paint. Polystyrene, that's probably accurate. And I will say, okay. There it is. I've finished fiddling with the parts. On the other hand, there's a couple things that are missing here. One thing that's missing is eye bolts. There should be an eye bolt right here at the base of the nose cone, and there should be another eye bolt right here at the top of this centering ring. So let me put the eye bolts in. They would be within the body tube, so I will call them a part of the body tube. Let me see if I can reach. There we go. I start out with a mass component. I'm going to call this forged eye bolt. And for reasons I don't fully understand, it often forgets the name if I do too much editing. So I just accepted forged eye bolt. And now I'm going to go back in and just say that these are 1 ounce components. And right now this 1 ounce component is drawn at the top of the body tube. And in fact, I want it to be down here. So I could have associated it with the nose cone, but one way or another, I want to place it at the base of the nose cone. So here is where it's located, and I can move it around. That's about where it would genuinely be located, just below the nose cone. So I'll say OK. And that's the upper eye bolt. If I do Control V, I can just duplicate it. And so now I have a second eye bolt, which has all the same features. But this particular eye bolt, I want to put down farther right here. Notice that it's right at the top of the centering ring. That's what I will tie my shock cord to. Okay, so here's the next thing I might do. I might think about stability. And right now the stability looks like 2.14, and that sounds healthy, but there's no motor in it, and I need the stability with a motor in it. So let me put a motor in this. If I click on Motors and Configurations, I will put the motor into the motor mount tube. I will say that I'm looking for a new motor, a new configuration. And it turns out that right now it's showing all motors for Aerotech and for Cesaroni. And I want to limit the motors to ones that would fit in this motor mount tube. So if I click here, it puts the upper diameter of the motor to 2.1 inches, 54 millimeter diameter. And now it has all motors 2.1 or smaller diameter. And if I turn this off and drag this over, I can actually tell it only give me the 54 millimeter diameter motor. So here they are. There's a lot of them. And I'm going to choose a 2-grain motor from Cesaroni. Let me find, oh, so these are all 1 grain, 1 grain. Here's the sort of the first 2-grain motor. It's a J145 motor. And I will say OK. In fact, when I say OK, I want you to watch 2 things. I want you to watch the location of the center of gravity will shift. The center of pressure will not shift. That's just based on geometry of the fins. But I am changing the weight, and the calipers, the stability, 2.14, will shift down because I'm putting more weight lower in the rocket. Here we go. Okay. Boom. So now my stability is down to 1.13, but the motor is in place. And if I was uncomfortable with that, let's say I was really hoping for a stability of 2, not 1, and certainly not negative, and maybe not less than 1. I can add some weight up here to draw the center of mass back forward again. So let me just try to do that. Let me click on the nose cone. Let me say that I want to add a mass component. I'm going to call this mass component ballast. Notice it's drawn at the tip of the nose cone. I will put it inside the nose cone next. So here is the location, and watch the center of mass and watch the stability. And so as I click up 1 ounce, up 2 ounces, 3, 4, every time I click, I'm getting approximately an extra tenth of a caliper. So now I'm pretty close to 2 calipers here, but I'm up to 9 ounces in mass, 9 ounces in weight technically. And frankly, 9 ounces would be bigger than that. So let me just assume that 9 ounces, made of fishing sinkers or something, might be in the vicinity of 2 inches by 2 inches. And I need to stick it inside of the nose cone. So it would sit right about there. And if I can only get it that far forward, I've lost a little bit of ground in my stability. So let me increase it to 10 ounces. 1.9, I'm okay with that. So I have 1.9 for stability by putting 10 ounces of weight, fishing sinkers perhaps, up here in the forward part of the nose cone. The way I would actually physically do that is I would cut a hatch in the nose cone. I might need one to install this eye bolt anyway to get a lock nut on it. And then I can take those fishing sinkers, 10 ounces, stick them maybe in a plastic bag, put it through the hatch and drop it all the way forward in the nose cone, and then stuff the rest of the nose cone full with like styrofoam packing peanuts or something to keep the ballast forward and not let it wiggle around. Now that I have my ballast in place and I'm reasonably happy with my stability, and I have chosen my motor, now let me go and simulate a flight. So I'm going to click New Simulation. And this version of OpenRocket is a little bit different from what I'm used to. But when I click New Simulation, it asks me for details about the launch location, including the wind speed. I'm going to leave that alone at 4.47 miles per hour, kind of light winds. The latitude and longitude, I would suggest that you put in the latitude and longitude for the launch site. So this is accurate for the North Branch launch site here in Minnesota. And the length of the rods, which happen to be 8 feet long, so 96 inches. And I would say save as default. Once you've put those numbers in for your launch site, say save as default. That way you don't have to keep putting them in every time you run. One thing that's missing on this screen that used to be here is run the simulation. So with this version of OpenRocket, apparently, you have to set the parameters and then you have to run the simulation from here. So let me say, if I say run simulation, it will just put numbers on the table, but I actually want to see the plot. So I'm going to say plot export, and it prepares to draw a plot with altitude versus time, velocity versus time, acceleration versus time. And I want to add a new feature. And the new feature I'm interested in is, this is a little different. It's a position motion type feature. I'm interested in lateral distance, which essentially is drift distance horizontally, to learn how far away this thing is likely to land under these wind conditions. Click plot. Here's what I see. First of all, it shows acceleration and velocity and altitude and lateral distance all in the same plot. That can be confusing. These are the numbers that apparently are going to be used for altitude and vertical acceleration, and the units would be feet and feet per second squared. And these are the numbers that are going to be used for vertical velocity and lateral distance, which apparently would be in feet per second and feet. I'm going to pay most attention to altitude in feet and lateral distance in feet. Here's what I see. The altitude in feet, which is this color, goes up just above 3,000. And then it ejects a parachute and it comes down at a constant rate and eventually lands here at 125 seconds. The lateral distance, it drifts away from me into the wind, and then it drifts back over my head. And so at 57 seconds or so, it's at 0 lateral distance. It hasn't landed. It's actually 2,000 feet up, but it's above the launch site. And then it continues drifting in that same direction under parachute and ultimately lands maybe 450 feet away. That's not particularly a long walk. You can definitely see a rocket that's landing only a couple hundred yards away. So if I say close and close, now I get some numbers in this particular table, which is important. First number that's very important is it coming off the rod at the rail in this case at a reasonable speed? That's defined to be 45 feet per second. So 71.8 feet per second, definitely this comes off fast enough. This has got very big fins, so I'm not too surprised by that. And it's a pretty long rail. But if you don't have your rail set correctly, the default rail length might be 36 inches and our rail is actually 96 inches, then you might be struck. It's like, wait a minute, that looks awfully slow. That's because you put the wrong rail length in. Apogee is just over 3,000 feet. At our club, that would mean tracking is required if you go above 3,000 feet. The velocity at deployment, the velocity at apogee, basically, it expects it will tip over a little bit, so it's moving, but not very fast. That's good. The optimum delay, that's the coast time, 7.5. So this motor, apparently, this is a 19A motor, so it comes with 19 seconds of built-in delay grain. And I really only want 7.5 seconds, so I will shorten up the delay grain a lot with tools. Maximum speed, maximum acceleration, time to apogee, which is just the coast time plus the burn time. Wow, this burns for a very long time. So it's coasting for 7.5 seconds, but it takes 12.5 seconds almost. So this is a relatively slow burning motor. Beware of slow burning motors on a windy day. The flight time is just over 2 minutes, 125 seconds. And the hit the ground velocity. This displeases me just a little bit. The rules are you shouldn't land faster than 35 feet per second, but in actuality, a good idea is to try to stay under 25 feet per second, lest you break something. And this is just a hair over 25 feet per second. So I could actually, and the reason that happened in part is because of this ballast. Here's what I'm going to do, just for fun. I'm going to take the ballast out. I won't erase it. I will just dial it down to be 0 weight. So now that it's down to 0 weight, my stability has suffered. But if I were to run a new simulation, notice that I'm not landing quite so fast and I'm getting closer to what I consider sort of this magic number of 25 feet per second. Another way to fight this, of course, since I put that ballast in for a good reason, is perhaps to include a bigger parachute. So if I go back to ballast, bring that back up to 10 ounces, and then go to my parachute, and you don't have just any parachute size available, but there are a variety of sizes available. For instance, I think it's possible to get a 48-inch parachute, maybe a 40-inch parachute. I'm just going to guess at this. But if I increase the parachute size just a little bit, new simulation, okay, got it. So if I only were able to get a slightly bigger parachute, I could bring that number down below 25 feet per second, which is what I would appreciate doing. So this is a look at an existing model, fiddling around, adding a couple components that weren't there, adjusting the components that are there to be more appropriate in material, in surface finish, in length, in weight, and in actuality. If it turns out that I have the parts in front of me and have weighed them all, I could go back and I could say, oh, by the way, that nose cone really is 5 ounces or 7 ounces. It's not 11 ounces as the model currently has. But this is good enough for a start. And you can continue developing it, evolving it, polishing it, making it more and more effective as you go. Surface finish in particular, it's hard to achieve really high quality surface finishes unless you have very fancy equipment. And that makes a big difference. And so right now I have smooth paint surface finishes and I might be over optimistic. In actuality, I find that OpenRocket and simulating programs in general tend to be slightly over optimistic in how high they think you'll go. Probably that's because you think you will have a higher surface finish than is actually built into the simulator. Okay, that's what I've got. A little bit more about OpenRocket.